Welcome back to this lecture series on microprocessor systems. So we are into the second last lecture, which is actually on analog digital interfacing. So just to refresh, where are we actually, like we do in the class, right? So we started our journey into the outside world. We started learning the interfacing options. We started off with, of course, GPIOs, the general purpose input output. It seems to be very easy to use tool. I hope you are also very thorough in that. Then we discussed about the timers and the interrupts, the options in that. They're also very crucial, even though they are not something which is useful for communicating with the outside world, but they are important for the internal communication, for example. Right? Timers are extremely critical. And interrupts is, of course, the better way of sensing or sampling compared to audio, right? And then we went into the discussion on serial communications. We had 3 separate lectures, one on the asynchronous protocol, which is UART. Then we discussed about the 2 synchronous protocols, SPI and I2C. Discussed among themselves what are the merits, demerits, and how do you go about it. And then I just want to ensure that you understood they are not limited to 3 serial communications. The modern day communications like Ethernet or USB or CAN bus that they use in automotive control, everything is based on these simple serial communication protocols. So it's important that you understand them so that you can easily migrate to the other protocols with ease. Okay. So here is something which is extremely useful in that aspect, because I don't know whether you realized it by now, or maybe this is the first course which introduces the analog digital interfacing aspect. You will learn about it in many other courses like analog digital communication, measurements and instrumentation, digital signal processing, etc. So many courses are there where you keep on hearing about this thing in more detail, maybe. Okay. So the world that we live in is analog in nature. Whatever you think about, the sound that you hear is analog because it is continuous over time, it is continuous in amplitude. Our ears are actually analog devices. Okay, so in fact, our human brain is one of the most sophisticated devices that you could think of, and it is also analog, it is not digital. Okay, so it is continuous. That is why none of the computers, even though they claim a lot, cannot replace human brain, or even not close to human brain in many things that you do. Okay, obviously, yes, you are beaten in chess, you are beaten in some other top games, but that's not the end, right? Human brain can do a lot of other things. So analog processing is important, and most of the things that you have outside world is analog. Temperature that you take, the heat wave that you take, the rain that you see, everything that you can think of are all analog in nature. Okay, but the thing is that if you want to sense them, you want to make meaning out of them using a computer, all the sound energy, light energy, temperature, pressure, whatever you can think of, you have to convert them into digital, convert them into numbers, and these numbers are what used in the number crunching machines like a CPU, a GPU, or an FPGA, whatever you can think of, right? So all the processing mostly nowadays is done in a digital because of obvious advantages, because digital systems are immune to the environment. Their storing is very easy compared to analog storing, where earlier we used to have magnetic tapes, for example, right? So those were very difficult. Okay, so as I said, everything in this world, whatever you think in the physical world is analog in nature. You name whatever you want. Okay, so everything. But there is a need to convert them into digital signals or electrical signals. There are various steps in doing that. The first step is that interface, where you have transducers or sensors or actuators the other way, which converts this type of physical energy into electrical energy. Okay, so for example, we have electromechanical type of sensing, photonic sensing, so on. And then examples, if you want to take microphone, which converts sound energy, which is a physical mechanical energy, into electrical energy, and a speaker which converts the electrical energy into sound, which is a mechanical energy. So that's a reverse form. So this is a sensor, this is an actuator, right? Microphone is a sensor, speaker is an actuator. Thermocouples, they convert the temperature into digital value for you to use, right? You might have seen the analog mercury-based thermo sensors, right? Thermometers. Then you have accelerometers where you measure the acceleration, convert them into digital values. That is what you have in your mobile phone. If you are very curious, please go ahead and do that. We do have one in our board also, Freedom board also, which we will read using I²C. Okay, so that is the concept. Okay, so this is just a concept note where we have light, sound, acceleration. Everything is analog in nature, but we measure it using some sensor or a transducer, convert that to electrical energy, okay, and make sense out of it. So this is the full list of sensors, maybe comprehensive, not exhaustive. And I'm not going to detail everything. I will upload the slide. Please have a look at it. So the possibilities are enormous. Okay, force, sound, position, acceleration, then something like battery, temperature, current monitoring. Okay, field. You are studying electromagnetic field theory, right? So all these sensors like Hall effect, variable reluctance, so many. Okay, location is important, right? So these sensing options that you have. And this is sort of a block diagram, I would say, a broad representation of your sensing phenomena, so analog to digital to analog. Okay, so you have the physical phenomena here like sound or light. You have a sensor here like microphone or the photodiode, which converts that physical phenomena into a current or voltage. But still this is analog in nature. That means it is continuous over time and continuous in amplitude, which is not representable in a system like computer, which is actually more of a discrete system, both in time as well as in amplitude. So use an analog to digital converter to convert this analog voltage or current value into some numbers. Okay, we can call it as ADC count, for example. Then you use software. This can be in FPGA, ASIC, or it can be in digital ASIC. When I say ASIC, okay, digital ASIC, FPGA, then CPUs, GPUs, etc. So you do a lot of processing. Okay, so then, in fact, both these can be combined. So you do that, you remove noise, for example, or you estimate something, for example, and then you how to give it back to the physical world is where you convert this engineering unit or electrical signal into a more continuous amplitude, continuous time analog signal, okay? Voltage and current again. And then you have an actuator, something like a speaker, which takes the analog voltage or current and makes it a physical phenomena like sound. Okay, so that is the whole phenomena that we look into. Okay, so this is your analog world, I would say, and this is the digital world that we or your generation live in, right? And this is the interface that we are talking about. Analog to digital and digital to analog. So let's talk about analog to digital conversion. You have an analog signal. The idea is like the time axis. This is a time. Okay. And the amplitude axis. This is your amplitude. Are both continuous. In the sense like I can have 0.000001 in the time. And correspondingly, that amplitude may be 0.00005. Okay, so it is possible. There is no precision associated with it. Okay, so continuous in amplitude, continuous in. Now, analog to digital conversion involves two processes. One is you first discretize the thing in time, which is known as sampling. So you won't take these continuous values in time. You only take values in a certain interval. For example, only at this point, this point, this point in time. Corresponding amplitudes only you will take. Something like this, okay? So at this instant, the amplitude from this plot is something like this. Then another point, then another point, then another point. So now no more this, continuous in time. This is discrete in time. This is continuous in time. This is discrete in time. Similarly, you discretize in amplitude, that is vertical direction. You define a certain number of levels, then you divide them into those number of levels, only consider those amplitudes, okay? So this is something which is discretized in amplitude, continuous in amplitude here. Okay, so that is the thing. So this is continuous in time, continuous in amplitude. This is discrete in time but continuous in amplitude. This is discrete in amplitude, continuous in time. Okay, so that is the thing. So basically you divide them into uniform intervals in time and in amplitude and take those values and you combine them. This is what you get, and that is what the digital signal that you are talking about. So they cannot take infinite number of values in time or in amplitude. There are certain positions of time and certain positions in amplitude, they exist. If something else is actually taken, it will be rounded off. So there is always an error. Please note that there is always a huge error when you go from this world to this world. Huge error. Okay, but we will leave it that because of the inherent advantages of the processing. Software processing is much easy, and inherent advantages of immunity to the environment and inherent advantages of storing the data. Okay, so let's actually spend some time in the first part, which is sampling, which is discretization in time. Okay, so you have the analog signal, which is continuous in time. You multiply them physically, or to easier for understanding, you multiply them with a series of delta or Diracs like this. Okay, they exist only at these uniform intervals. Let's assume this this time, whatever is the time interval, is Ts. Okay, capital T, small s. Okay, suffix x. So that's a uniform time interval. So I only consider the values at 0, Ts, 2 Ts, 3 Ts, 4 Ts, and so on. And that is what I have it here. So let x of t be the input signal, which is continuous in time. G delta of t is the delta series of the series of delta functions separated by Ts time interval. And y of t is the output, which is discretized time signal. Okay. Now in mathematics, y of t is nothing but the product, the dot product of x of t and g delta of t, right? Simple multiplication. Okay. Now if you see this one, if you go back and see your signals and systems, you understand that this is a series which is a periodic function in time, correct? So that can be expressed in terms of its Fourier series, right? Anything that is periodic, which is repeating with time Ts, which is infinitely long, this can be represented in a beautiful algebraic expression in terms of its frequencies as this. Okay, so all I did in these two equations is I converted this into a representable equation, right? This is infinitely long, right? It can start from minus infinity to plus infinity. It can be represented by its Fourier series, which is also infinitely long, but this summation is very beautiful because it can be represented by a mathematical expression. So G delta of t is nothing but 1 over Ts. Ts is a time interval. E raised to j 2 pi n fs t, where fs is nothing but 1 by Ts, and t is that duration which is infinitely long. Okay, and then n varies from minus infinity to plus infinity. So I just represented that in terms of its Fourier series. Now, if what I need to actually know, I'm taking you to frequency domain, which is, this is time domain. I need to see the frequency of a particular signal, for example. Here I'm just showing you a nice sinusoid, but in our case, it can be something which is deviating from a sinusoid. It can have multiple sinusoids, for example. So let's take Fourier transform on both sides, x of t and y of t. Okay, so what I'm going to do, y of t, Fourier transform, let it be represented by y of f, and then right hand side is the Fourier transform of this entire product. Okay, so x of t into 1 by Ts into this. Now in this case, I can take these two terms, 1 by Ts into this outside, and then put the Fourier transform of x of t into this inside. And if you do that by simple mathematical reformulation, I'm not going to the derivation. You can always go back and check. It's very easy. So what I did is I took this part out that is shown here, and then Fourier transform of x of t into this particular thing. This into this is something like what you call, it's actually a frequency shift which will reflect as phase shift in the frequency domain, correct? So that's what actually happening. So the meaning of this is x of f is the frequency spectrum of this case, this guy, x of t. But when you do the sampling, or when you do this sort of a process, sampling in time, what essentially it does is x of f is repeated. X of f is no more at x of f alone, but it gets into n fs. So let's say n is 0. That means this term vanishes and this will be x of f itself. Okay, and then it will be at x of f minus fs, x of f plus fs, x of f minus 2fs, x of f minus 2fs, infinitely long. So that is the most important phenomenon. So analog signal has a spectrum x of f. Let's say, let's ignore this comment for a moment. Analog x, let's say its spectrum looks like this. When I go to Fourier transform and plot it, so the x-axis is the frequency, y-axis is the corresponding magnitude. If I plot it, let's say it is looking like this. It has a bandwidth of minus b to plus b, total spread. So bandwidth of 2b. So this is the spectrum of x of f. But moment I sample it, y of f is no more along at this position. It will be at all the multiples of fs. So let's say this is 0. That's what it is standing for, x of f minus 0. That is what this location stands for. It will be existing at x of f minus fs, f of f minus 2fs, 3fs, etc. And similarly f plus 2fs, 3fs, etc. So it is something like this. So just put it in the pen option. Okay, so this is your x of f. Okay, is your friend s of f plus fs, and this is your friend x of f minus f, capital Fs. Okay, so and so on, you can have this point and this point. So what you actually observe is when you sample, the spectrum is getting replicated. The spectrum is no more at this location alone, but it be at fs, minus fs, 2fs, minus 2fs, and so on both sides. So if assume that this is not band limited like this, if it is really spreading, let's say it was like this, then what about minus fs, 2fs, 3fs, etc.? It will all get distorted, right? You have the spectrum coming something like this, it gets totally disrupted. You don't want that. So that is why it is important that before you do sampling, you do something like a filter which will limit the spectrum to, let's say, between minus. Okay, so I'm just rubbing all the things off. So what this statement actually tell you is, this statement tells you is, this spectrum has to be band limited. The original analog spectrum has to be band limited. If it is not band limited, the sampling process will distort the spectrum. So it's important. Now, there is something else also you have to be thinking about, right? What is this TS? How small I can go, or how bigger I can go for this TS. So there is a relation. So TS and Fs are related. These Fs and Ts are inversely proportional. Fs is nothing but 1 by Ts. So let's see different scenarios. Okay. So according to, there is something known as Shannon-Nyquist sampling theorem. This Fs should be at least greater than or equal to 2 times this total width. So that is important. So let's examine that. Okay. So this is your original signal again, and these are the possibilities or the repetition that will happen after the sampling, right? So let's think about this scenario. Fs is exactly equal to 2f. That means this distance, okay, this distance is exactly equal to 2f. 2f is nothing but this bandwidth. Okay, so okay, so let's put that way. So this distance is 2f or 2b, whatever you want to, both are equal. Okay, 2b, this distance. So if it is exactly equal, you know that your signal is something like this, right? So minus b to plus b. You have a perfect fit, right? It's a tight fit. Nothing is a problem here. It exactly fits. And if you want to recover the signal later for the DAC, you just need to put a filter like this. and you are able to recover the spectrum. Okay, but now imagine a scenario where Fs is less than 2f. That means you have a crowded spectrum like this, and you have a problem. Okay, so it gets distorted. The best scenario is you have Fs much greater than 2f, and you have a lot of relaxation space here, right? This is a space for relaxation. Okay, so that is the criteria. So when you specify the sampling rate, it should be actually at least twice the bandwidth of the input spectrum. And you can control the bandwidth by putting a filter. So before the analog to digital conversion, you put an analog filter, control the bandwidth. Let's say your bandwidth is controlled to be 2 times B, then your Fs should be greater than 2 times 2B. Okay, so that's the concept. The second aspect, so we talked about sampling in time. Now there is sampling in amplitude, right? So let's say, so this is more towards that number of bits that you use. Let's say you have an 8-bit ADC. So that means you are going to sample your input signal with 2 raised to 8 levels. So your amplitude is divided into 2 raised to 8 values. Okay, so that's the meaning of it. So anything in between these 2 raised to 8 values, you have to round it. There is an error. So that is a problem. Okay. And then there's a more important aspect to it. So there is a span, right? How much should my voltage range span? For example, this is your input signal. So this is your input signal. And shall I span my range from VR minus to VR plus? No, because the range is too small. This part is gone, right? This part is gone, and this part which is outside is also gone. Shall I do this way? Much higher range? No, because then in this case, for example, the range is not a problem, the span is not a problem, but then you are going to divide, let's say 2 raised to 8 levels. You are going to divide VR minus to VR plus into 2 raised to 8 levels. But then these regions are completely wasted because your signal is only restricted in this small region. This region is gone, it's a waste, right? So that's also not correct. This is sort of an ideal fit. Now a good fit VR minus to VR plus the span, and then you are going to divide this range into 2 raised to 8 levels, for example. In this case, no problem. So the range is a very, very important aspect. The span of the signal or the span of the ADC when you choose is a very important aspect. Okay. So now once you select the range, this is how that quantization or the sampling in amplitude happens. So in this case, I'm showing a blue signal, which is an analog ramp. Okay, so this is a ramp signal which is increasing, and on the y-axis I'm showing you the level. So here I'm talking about the 7 or 8 bits that I have. So 2 raised to, I'm sorry, here it's a 3-bit case. I'm sorry. So this is a 3-bit case. So 2 raised to 3, 8 levels. So 0 to 8 level, you can see over here. And the important aspect is like, let's say I'm going to sample at this interval, this interval, this interval, this interval, and so on. So in this case, I'm going to sample at this point. And this point is not in 001 or in 000. So you have to round it off to one of these, and you normally round it off to the closest value. So it takes this value. So for example, here, in this case, this is the point. This value is closer to this 011 than 010. So in that case, I will round it off. So whatever value, I will round it off. That is an error. That is the quantization error. And that is actually rounded to this. Okay, so this quantization error is important because it induces a noise in the signal. Okay, so this is a very, very important scenario. So when you sample in time or sample in amplitude, you are inducing an error. Okay, always remember that. And uniform quantization typically means you are rounding it off to the closest value, and you use a round operation, and you round it off to the closest value, and there is an error associated with it. And you will study in detail in DSP, for example, how to quantize that error. Okay, and higher the number of bits, obviously you'll have more finer levels, less quantization error. Okay, so that is obvious. So that is why you typically want to go as many high number of bits as possible. Now, how do you implement this? That's very important, right? So here is, I'm going to introduce a very, very trivial flash converter. Okay, so this is your input signal, which is actually connected, and this is connected to the one of the terminals, let's say positive terminal of an operational amplifier. Okay, so this is a differential amplifier. The other input is actually fixed. Okay, so there is a Vref voltage. This is a range that I was talking about. VR minus to VR plus, for example. So this is a reference voltage that I'm going to. This is a very simple example. So we are going to divide it into 4 levels. So this is sort of a 2-bit representation. Okay. So level, this is one level, which is highest, next highest, next highest. So this is sort of the ground level, right? So let's see how it works. So an input voltage comes here. Okay. Same is given to these 3 comparators. It will check with the corresponding reference values. Let's say this input voltage is greater than or equal to this value. So that means this will be enabled. Okay. So 3 will be enabled. So corresponding bit value 1, 1 will come out. Similarly, if it is actually greater than this 2 summed value, then obviously this will go. Okay. So that bit will come. So that is how it works. The voltage value may be increasing. It will be checked with all these. Whichever is the closest match, corresponding bit will be output. Okay. So something like this, for example, I'm just goes here. So 4 volt, 3 volt, 2 volt, 1 volt, 0 volt, and 2.5 volt is my input value corresponding. Okay. So you just see here 2.5 to 1. This is high, right? Higher. This is also higher. This is lower. Okay. So it will go for the. This is also high. So this will go for the highest of this. So you just see here 0, right? This is only 0, and that value will be, and this is the highest value out of these 2. So that value will be out. Okay. Hope it's clear. I'm not confusing you. It's quite straightforward actually. Okay. But this is very trivial, right? If I want to increase the number of bits, then I need to increase the levels. No, that is not the solution. So this is a modern day ADC, which is based on successive approximation. So I will simplify it for you. So you have a successive approximation register. SIR stands for successive approximation register. There is a clock here. This will produce an, let's say, an n-bit output here. And there is a DAC which will convert this n-bit value into an analog signal. Okay. Based on some reference value that you give. That analog signal will be compared with the input signal. Okay, so this is sample and hold. This is a sampling process. So you have to sample the signal and hold it for some time so that the sampling in amplitude happens. So that is why the name sample and hold. Okay, you sample in time, keep that value for some duration of time till the sampling in amplitude happens. Okay, so that is typically the meaning of it. So some input signal is coming, let's say. Okay, so let's start with 0. Okay, so 0, all these are 0. So you'll have a 0 value coming out. You are comparing with that. And if it is greater, you'll have some error signal coming. So that error signal will get converted into a digital value, right? Whatever. And then that will be again converted to an analog value. Then you compare. So you can think of something like it is increasing from all the zeros till all the values goes. And then based on that, corresponding bit values, whatever bit value, minimized bit value, minimum error value, that will be taken as the output. So there is a problem here because let's say there is n number of bits in a sample. So it requires n cycles, right? Because first I will be checking for this bit, then this bit, then this bit, and so on. So based on that, for n bit, you need n cycles. Okay. And it goes from MSB to LSB most of the time because it may go according to this phenomena. So it goes from MSB to LSB. If this is low, check for this. If this is low, check for this, and so on. Okay. So if it is high at any MSB, that bit is set as 1. Okay, so that is how it works. So we'll set the MSB as 1, check for it. Next MSB as 1, check for it. So which is closest highest, you set it as 1. So that's the thing. It is not good for high-speed ADCs. So you have other options. Please look for that. You will study that in detail when you study measurements and instrumentation. Okay, all the different types of ADCs. Let's move ahead. A small trivia for you, and I would like to pause for a moment. You just pause it and try to answer for yourself. I have an input analog voltage which is ranging from -5 to +5 volt. I'm going to use a 10-bit analog to digital converter. Calculate the number of quantization levels calculate the voltage resolution. I suggest you to pause the video and answer this. Okay, so you might have got the answer. So how many levels? This question, how many quantization levels? You have a 10-bit, so it is obviously you will be dividing the voltage range into 2 raised to 10 levels, right? So 1024 levels you have. What is the voltage resolution? What is the voltage resolution? You are ranging from -5 to +5. So 5 minus -5. So that is your voltage range. And you are going to divide that by 2 raised to 10. Okay. So this will be nearly equal to 9.76 milliwatt. Okay. So that's the answer that you should get. So voltage resolution is nothing but the total voltage range, which is 5 to -5 divided by the total number of levels, right? The entire voltage range, you are going to divide it into 2 raised to 10 levels, and that is 9.76 milliwatt. Okay. Now DAC, we talked about analog to digital converter. This is digital to analog converter. Okay. So this is just the opposite of that. For example, you give a digital input, it will have a decoder. So each one of these will be checked. Okay. So let's say 0, 0, then this value, right? Because this is enabled. So this value will be coming at the output. If it is 1, 0, this will be enabled. I'm sorry, 0, 0, ground will be enabled. So 0 will be coming at the output. 0, 1, this will be enabled. Whatever voltage drop across this will be enabled, and that will be coming at the output, and so on. This is much easier to understand. Okay. So that is the DAC. And this is how the ADC looks like in your KL25Z board. I'm not going to discuss on this in detail. It is self-explanatory. This is using the SIR, successive approximation register method. And there is no point in understanding it in very thorough unless you're going to modify it, right? Our job is just to configure the registers and make it working. And that is very easy. I will show you the code for it. And then this is the DAC part as well. Again, similar to the register example, the DAC example that I was showing you here. Okay. So let's quickly go. I will upload this example anyway in Moodle. And this is a free trial for you. This is experiment which you will be doing, which is not value, basically not evaluated, but I suggest you to do this. So these are the analog input and analog output. So this is the ADC pin PTE20. Okay. And this is actually the output, P30. Okay. And there is certain conversion rate, for example, V into this is important because when you have the voltage measured, if data is your this is basically to convert that the scaling factor, the digital value which is measured inside in terms of the reference value that you need. Okay. So in case of our board, Vref is 3.3 volt total Vref. And then based on the value that you get, you can find out what analog voltage it represents. Okay. This is a digital value, 12-bit digital value, for example. Okay. And this 4096 comes from this 12. Okay. This goes back to the trivia question. Okay. So this is not magic here. So given Vref, okay. So what is that value that you measure? So this is an example. So here we have it. So the ADC 0 pin, I'm going to input a potentiometer, something like this. So you give the voltage to the potentiometer 3.3 and ground. The middle pin is given to the PTE20. That's what I was showing you here, this pin, PTE20. Okay. And this is a code, how it looks like. Of course, you have to include the header library where all these are initialized, ADC 0. So this is the initialization for the ADC. Then this is just to set some LED. And this is actually to initialize. So initialize this input. Okay. So let's see how it looks like. So in the main, I'm going to actually initialize the ADC and this. So let's actually see how the ADC is initialized. So this is actually to set the clock for port T, because that is the port I'm going to use it as input, right? That is the multiplexed pin for the analog input. And then port is 20th pin. Okay, so that is configured as analog input. Okay, so you do that. And then this is to enable the clock for ADC 0. Okay? And then this is actually to set up. So please go through the manual and understand what the steps we are doing over. So this is to configure your ADC. So once the configuration is done, okay, this is just to display some LED, and also you can ignore it. Okay? But I suggest you to do this experiment in the lab, as well as if you have board with you, you can do that. I will upload this document. And then what essentially this step does is it initializes the GPIOs, it initializes the ADC, and then it reads the value here. Okay? So this is the value which is read, the result, okay, and then display that result, whatever is the value on the LED. And similarly, I have the option for the DAC, where you're giving some value here and you're going to display that the analog value in an oscilloscope. So these two experiments is quite self-explanatory by now. I should not spoon feed you and try to make you understand what each of these means. You should be able to understand it by now. If